Hello and welcome to this section of the chemistry tutor. Here we're going to switch gears from acids and we're going to begin to talk about bases. And I already hinted earlier that acids and bases are kind of opposites of each other, and we'll talk about why a little bit later. But for now we need to define what a base is the same way we defined an acid. So the way we're going to do that is by writing a definition that we're kind of like what we did last time. So a base is a substance that produces hydroxide ions. These are the ions that look like OH negative, like this, in aqueous solution. All right. They produce hydroxide ions. So just like the acids, you put them in water and they produce hydrogen ions, right? That defines an acid. A base is a substance that when you put it into water, it produces these OH. Notice OH is one of those polyatomic ions we talked about a long time ago, and they exist as a unit, and the total charge on this unit, this OH unit, is a -1, right? So that's called a hydroxide ion. So when we say it produces hydroxide ions, that means if I sprinkle this substance that I'm calling a base into water, then it should dissociate, and some of the stuff should go out as OH negative ions, and then whatever else the base is made of will also go into solution as well. So just like HCl, hydrochloric acid, breaks into hydrogen ions and chlorine ions, the bases will break into these hydroxide ions and something else, depending on what the base actually is. So as another characteristic, we talked about acids being sour. Bases are bitter. Now, I want to stress that this is if you had a really weak base, something that you could taste, something that was really weak. But just so you know, just like you can have strong acids that can be corrosive and hurt your skin, there are strong bases that if you get them on your skin will definitely burn you just as much as an acid. So acids and bases really can both be very caustic. They can hurt you, especially if you have a strong one. So don't go thinking, oh, bases are no big deal. It's not like an acid, right? It's not like that. Acids can be strong, they can hurt you, they can be corrosive. Bases can really do the same thing. But if you had a really weak one, then it would taste bitter as compared to sour for the acids. All right, now for acids we said, okay, we have the idea of what an acid is, and we said, okay, if we had a strong acid, that is a substance, when you put it in water, it dissociates completely, breaks down completely, so there's lots of ions floating around, and so it's a strong electrolyte. So we're going to have a companion definition that's going to basically be true of strong base as well. So let's talk about that. Strong base. What do you think that might be? Well, it's a substance that completely ionizes in water. So they are strong electrolytes, and they, of course, conduct electricity. So the definition is basically the same. If you have a substance that's a base that breaks down fully into these hydroxide ions and then whatever else the base is made of, then there's lots of ions that are going to be floating around solution. So because of that, they can conduct electricity well, and we call that a strong electrolyte. So the bottom line is the strong acids are also strong electrolytes. The strong bases are also strong electrolytes, and that just comes about because they break down readily. So let's give an example, a real example of a base. Probably the most common base that you'll hear about is sodium hydroxide, NaOH, sodium hydroxide. You'll talk about this. So let's say it's a solid. Usually you get them out of the, in powder form or in pellet form. And let's say you put it in water. What do you think is going to happen? Well, we know that if it's a base, it has to break down into these OH hydroxide elements. So the only other thing other than OH is the sodium. So what we're going to have is the sodium break down into its, or ionize into its positive ions, course, it's an aqueous solution because it's now in water. And the hydroxide ions are also an aqueous solution. So this is what a dissociation would look like for sodium hydroxide. So you know from the periodic table that sodium has a charge of +1 when it ionizes, and you know from looking at your table of polyatomic ions that we talked about a long time ago that this unit here, when it breaks down, has a charge of -1. So that's why we have a -1 here and a +1 here. Notice that everything's balanced. One sodium, one oxygen, one oxygen, one hydrogen, one hydrogen. We don't have to put any numbers anywhere. Depending on the base or the acid or whatever you're talking about, you may need to balance it here, but we don't need to do that because everything's already done. Now notice that this arrow here is only going one direction. It's pointing to the right. That means that as I put the strong, this is a strong base, as I put the strong base in water, it's breaking down spontaneously and completely into sodium ions and hydroxide ions. The arrow is not going the other way, and that means that these guys are not wanting to join up again and form the stable unit. They just sort of love to break apart, just like, you know, salt is a ionic compound that you put it in water, it loves to break apart. It's not going to come back together and form salt crystals inside of water. So this arrow is going one way, so these two guys are not going to want to go back and form the solid. It breaks down entirely, so that's why it's an example of a strong base. So now that we've talked about what a strong base is, notice we're kind of cooking along a little faster now that we've got some of these basic concepts out in the last section. You should already know what a weak base is, what the idea of a weak base is, just because of the context here. So it's basically a base that only some of the molecules ionize. So you're not getting full ionization. So because of that, what happens? Most of these remain as intact molecules. Okay, and so because of that, because we don't have full ionization, that doesn't conduct electricity very well, so we call it a weak electrolyte. All right, so this basically follows everything that we've been talking about before. And I'll give you an example of a weak base here right now, but at the same time that I'm giving you the example of a weak base, I'm going to give you an example of sort of a special base that doesn't quite, it produces hydroxide ions, so it's a base, but it doesn't quite look exactly like this one, and it's sort of an exception to the rule. You might see it in your book, so I'll just go ahead and kind of illustrate what's going on here. If you take NH3 as a gas, okay, and then you put it in water, right, then what you're going to get, I'll just kind of draw a little arrow down here. What you're going to get is NH3 in aqueous solution. However, whenever you add this, when it's all in with an excess of a bunch of water, there's actually a chemical reaction that likes to form here. So most of the time when we put these bases in water, there's not really any chemistry going on. It's not combining with anything else. It's just breaking apart, and then that's that. Here, when we put this ammonia, this is ammonia, when we put ammonia in water, then what's going to actually happen is it likes to react with the water. So what happens is one of the hydrogens gets pulled off of the water and gets stuck onto the ammonia. So what you get is NH4. What do you think is going to happen? Once one of these hydrogens comes over here, hydrogen ion has a charge of +1. So if a hydrogen ion comes and gets stuck onto this molecule, then this ammonia becomes an ion, and it's called an ammonium ion. All right? And then also, because one of these hydrogens came over here, the only thing you have here is HO remaining, which if you flip it around is OH. And the charge of OH is always negative. Okay? So these are both an aqueous solution. I guess I should make sure that you understand that. So this is an aqueous solution. This is an aqueous solution as well. So this is just another way that a different substance is forming a base. So typically, 99% of the time, all you need to know is it's a substance you get off the shelf, you put it in water, it breaks apart, right? Some of it goes into whatever the other metal is, and some of it goes into hydroxide ions. This is a special case. If you take ammonia and you put it in water, it doesn't just break off. See, notice there's no OH here. See, normally in the bases there's an OH somewhere around. It just wants to break apart in water, but ammonia is different. There's no OH anywhere here. But this is a special substance. When it goes into water, it strips a hydrogen off the water here, making it a positive charge, and then what's remaining behind is a unit bound called a hydroxide ion, same as before. So basically it is a substance that follows this definition, that when you put it in water, it produces hydroxide ions in aqueous solution. It is a substance, when you put it in water, through whatever means, it produces hydroxide ions. So it is a base because of that. Even though it's not bound up and it doesn't break apart and produce it directly, it likes to create hydroxide ions in solution, even if it's indirectly through a chemical reaction, so we call it a base. So that's what's basically going on here. All right. Now, the only other thing that's funny about this is, notice I have an arrow going this way. That's telling me that the ammonia likes to react with the water, giving ammonium ions and hydroxide ions. But also, this is actually a weak base. I haven't really told you that explicitly, but it is a weak base. So the arrow here, if you look in a chemistry book, actually goes both ways. And this might be the first time you've ever seen a reaction that can actually go both ways. This means that half of the time, roughly, or whatever, this is combining with water to yield this. But the other half of the time, these things are floating around in solution. They like to combine back together and give me what I started with. So what's happening is, some of these things are reacting, taking the hydrogen and producing this, and these things are coming together to produce this. So in this case, what's happening is a hydrogen's coming off of here, going over here, forming HOH, which is H2O, that's water. So a hydrogen goes over here, forms water, and you're left with NH3. So you're left with NH3 plus water. So the reaction is going this way, and the reaction is going this way. And we'll learn about this a long time in the future, but when you have bidirectional reactions like that, what happens is you reach a balance point where everything kind of equals out, because some stuff's trying to go this way and form products. Some products are trying to combine to form reactants. Eventually you reach some kind of steady state where you reach a concentration where, yeah, I'm producing the products and I'm also combining to produce the reactants, but everything has basically reached what we call equilibrium. It's reached that steady state where the concentration of everything doesn't change anymore, but the reaction is going this way and going this way basically at the same time. But for the purpose of this section, for the purpose of this class, this lesson that we're talking about on bases, I'm just telling you that an example of a weak base is when only some of the molecules ionize, most remain as intact molecules. Ammonia likes to remain as an intact molecule as much as it can. Some of it does react with water to produce this, but these things like to combine to produce the molecules. So it's different than this sodium hydroxide. Sodium hydroxide, it doesn't want to form. This ion does not want to come here and form sodium hydroxide solid in water. It just doesn't like to proceed that direction. But ammonia is a little bit different. So just keep that in mind. You might see that as sort of like a side example on another example of a base. So at this point, I think we're ready to make a listing of some strong bases and weak bases, just to give you that exposure. So strong base. Strong bases. So we'll go ahead and make a quick listing. And the most common one is one we've already talked about, sodium hydroxide. Sodium hydroxide. All right, and then another really good one that you see a lot is potassium hydroxide. Potassium hydroxide. Notice they all have hydroxides bound up. Another example, another common one, lithium hydroxide. All right, and then another common one is calcium hydroxide. By the way, why do you think that it's a 2 out here? The reason is because for all of these three top ones, these all, sodium, potassium, and lithium on the periodic table all have a charge of +1. The hydroxide charge always has a charge of -1. So to make a intact structure here, if you go back to our very first lessons in chemistry, you kind of do the crisscross thing. Then you have NaOH, KOH, and lithium hydroxide. Here, if you look at the charge of calcium on the periodic table, it's +2. And this is -1 for hydroxide. So if you do the crisscross thing, then you get a 2 down here and a 1 down there to make a neutral ionic substance there. All right, so those are some examples of some strong ones. Let's look at some weak bases. Weak bases. Probably the best example is one that we've already listed, NH3. We call it ammonia. All right, now this is, by the way, a household cleaner. So you probably heard of ammonia. It's something you can actually get in at the grocery store, and you could take it home and clean your floors with it. And it's, it is a base, but it is something that can clean things very well. Now, we did talk about briefly that ammonia is something that behaves slightly differently in the way that it produces the hydroxide ions, but it does produce hydroxide ions when you put it in water, so it is a base. And it's a weak base. All right, and finally, another common one is something that I know you probably have in your house. It's NaHCO3. This is sodium bicarbonate, otherwise known as baking soda. So that's why I say I think you might have that in your house somewhere. All right, so that is also a weak base that you have hanging around in the refrigerator or in the pantry or whatever. These guys are weak though. They like to remain as much as they can in terms of their intact molecules, and that's why they're not strong bases. If you put them in water and they completely break apart and they do not like to retain this form, then they totally dissociate. We call them strong bases. So that's what those are. These guys, yeah, they do break down. They try to form the hydroxide ions, but the reaction's also going in the reverse direction. So it's trying to at least some percentage, is trying to remain in its original molecular form. So believe it or not, we're done with this lesson. I just wanted to introduce and make sure you understand what a base actually is. And basically, it is a substance, when you put it in water, it produces hydroxide ions. And that's different than water, because different than acid, because acids are substances that produce hydrogen ions. And so we can classify these bases as strong bases or weak bases, just like in acids, and it all boils down to how much it dissociates, how much it breaks down. And what you'll find out later is the concentration of this hydroxide ions in the solution dictates how strong the base is. So the more they break down, like these guys, the more hydroxide is going to be produced, so the stronger the base. These guys don't produce as much, that's why they're called weak. And of course, because these break down completely into these ions, they conduct electricity well, they're called strong electrolytes. And these are basically weak electrolytes because they don't break down as much. They don't exist in ionized form in solution as much. Notice most of these bases are just a metal plus a hydroxide ion, and that's mostly what you're going to see. There's a whole laundry list of additional bases that we could write down. Lots and lots and lots of bases we can write down. But these are the most common ones that you'll typically see in your chemical reactions. Now let me close the section by giving you a little bit of a preview to where we're going here in the next few sections. Let's look at the duality here, okay? Acids produce H+, hydrogen ions, right? Bases produce OH negative, right? Negative charge, OH. So again, I'll say acids produce hydrogen, H+, and bases produce OH, which is negative, right? So if you take an acid that has a lot of H+ ions floating around inside of it, and then you take a base that has a lot of OH negative ions, and then you put them together, what do you think is going to happen? Well, you have the hydrogen here combining with the OH here, HOH. HOH, what do you think that is? HOH is another way of writing H2O, water. Okay, so when you take an acid, has lots of hydrogen ions, and you take a base, has lots of hydroxide ions, and you put them together, they're going to want to react so badly. Why? Because it wants to form water, right? Water is one of the most stable molecules we have. Our planet has tons of water because it's so stable. We have most of the planet is water, right? So water really, really, really wants to form badly. It's very stable. It hangs around for a long time, right? So if you have a substance with lots of hydrogen ions and they have another substance with lots of hydroxide ions and put them together, you have everything that you need for H2O water. And that's basically what's going to happen when you combine an acid and a base together. They love to react so that they can form those water molecules. And that's where we're going in the future. So keep that in mind. That's when I said acids and bases are kind of opposite, because they're kind of like one half of a nice reaction that we're going to talk about later to basically form water. And these kinds of reactions are happening in your body, they're happening in nature, in the environment, so they're very important. Acid-base reactions are where we're going next, and that's why they're so important, because they're so common. So make sure you understand what a base is, make sure you understand what an acid is in the last section. Follow me on to the next section where we'll start talking about how these two guys interact together.